So in the previous module or the previous video, I did define the terms percent yield and atom economy. But in this section, we're actually going to start using them. So both percent yield and atom economy are used as methods of measuring the success of a reaction, but they're again measuring different things. So the amount of product collected at the end of a reaction is called your actual yield. How much did you actually obtain? And this is often less than we predict you should be able to obtain or get based on, and this is based on stoichiometry, which is called your theoretical yield. So doing a calculation tells you how much could you theoretically produce. However, what we find is that in most reactions, we don't actually make that much. We can have side reactions, we can lose product and purification steps. Some reactions don't go to completion. We have equilibriums. All these things can happen to make a reaction not go and produce what we think it should produce based on what we put in. So the two different concepts we want to look at here, percent yield and atom economy. Percent yield is what's comparing your actual yield to your theoretical yield. Theoretical yield involves a stoichiometric calculation. That is what you get from doing that full calculation saying this many grams of reactant makes this many grams of product. That's your theoretical yield, and it always goes in the denominator because it's how much you could theoretically make. You're trying to figure out what percentage of that did you actually make. So actual or experimental yield will go on the top because I want to know, comparative to my theoretical yield, how much did I make? How much product should you theoretically obtain or yield from the reaction? So percent yield is really just looking at the success of a reaction with respect to one reactant. I wanted to make this much. How much did I actually make? Atom economy, on the other hand, looks at the molecular weight of your desired product divided by the molecular weight of all reactants times 100%. So this one doesn't actually look at how much was actually produced. This one looks at how much could theoretically how much do I theoretically want out of everything that goes in? I threw all this in a pot. How much do I want that comes out? Not how much do I actually get out, but how much of what comes out do I actually want? So the reason we have a picture of M&Ms here is to show us an example with M&Ms. Let's say that, I'm not going to actually count all those M&Ms anymore, but let's say we have 20 M&Ms. We put a recipe together to make 20 M&Ms, but what we really want is just the green M&Ms. Let's say there's 5 colors of M&Ms, and I know that there's more than 5 colors, but let's say we're only making 5 colors of M&Ms. And we've calculated that out of our 20 M&Ms, just simple division, 4 M&Ms should be green. Okay, so we know that we should have 4 green M&Ms. Let's say I do the reaction and I obtain at the end just 2 green M&Ms. So I take 2 divided by 4, multiply that by 100%, and that would be a 50% yield. That means I got half of what I thought I would. On the other hand, atom economy. It looks at the molecular weight of the desired product divided by molecular all reactants times 100%. In this case, we told you we think we should be able to obtain 4 green M&Ms. Let's say M&Ms all weigh the same, so we want the weight of 4 green M&Ms. We divide this by 20 M&Ms total times 100%. So 4 divided by 20 times 100% gonna give me 20%. These are both important calculations. Again, percent yield, how much did I actually make that I thought from what I thought I could? Atom economy, what is the percentage of what I actually want comparative to what I put in? Most often, you're going to find percent yield being used as your measure of an efficient reaction. Atom economy is a newer concept. It falls under the purview of green chemistry and sustainability, so it's becoming more important to consider that going forward in science today. But percent yield's been around longer, and we just use it more often. So I'm going to focus more on percent yield in here, but atom economy does still kind of play an effect. First thing that throws students off is, why is the yield of a chemical reaction never 100%? Well, as I stated in the previous slide, reactions don't always go to completion. We have this thing called equilibrium, and we're going to study equilibrium really heavy in second semester, but we will touch upon it in this semester. Some reactions go to a certain point. They reach this point, and at that point, the reaction can go forwards or backwards, meaning the reactants can make more products. Those products can react to kind of convert back to the original reactants. And they find the sweet spot in the middle that they want to reside in, and it's called their equilibrium. You can have impure reactants. When I buy a chemical from a chemical supply company, it's not 100% pure. The more pure it is, the more expensive it is. Buying a chemical that's 98% pure, but a good price, is a lot more efficient than buying a chemical that's 100% pure for 10 times the price. We can also have side reactions that form other products. We don't talk a lot about side reactions in Gen Chem, but if you take organic, you're going to see this a lot. We can also lose product through filtration, through being lost in a beaker, etc. So usually that comes sometimes in the reaction itself, but a lot of times what we call your purification steps. We've made a product, now we need to purify it because we need to separate it out from that unreacted or impure reactants, anything left behind by the reactants, any side reactions, etc. We can also have a reaction that's over 100% yield. Usually that means it's still wet. It still has solvent present. In Gen Chem, your solvent is usually water, not always, but it will sometimes be over 100% just because it's still wet. So let's go ahead and work this example. We've got magnesium carbonate decomposing on heating. So magnesium carbonate decomposes on heating, and it forms magnesium oxide and carbon dioxide. We're going to have to put together a reaction here. Suppose 50 grams of magnesium carbonate was heated and 20 grams of magnesium oxide was subsequently collected. What is the percent yield of this reaction? Well, let's first figure out our balanced reaction. Magnesium carbonate. Magnesium is Mg2+, carbonate is CO3 2-, which means magnesium carbonate is MgCO3. This decomposes on heating, so I put a little arrow for the separate reactants and products, a little triangle on top to represent heating, to produce magnesium oxide and carbon dioxide. I started with 50 grams of magnesium carbonate, and I collected 20 grams of magnesium oxide. And I want to know, what is my percent yield? Well, remember percent yield is calculated by taking your actual yield and comparing it to your theoretical yield and multiplying that ratio by 100% to put it into percent form. Theoretical yield is what you're going to get from your stoichiometric relationship. So, how many grams of magnesium oxide could I theoretically produce if I decompose 50 grams of magnesium carbonate? Put this into moles. 1 mole magnesium carbonate. The molar mass of magnesium carbonate is 84.32 grams. Now convert mole to mole. When you look at your balanced reaction, it's really easy to balance this one. Everything's 1 to 1. So 1 mole magnesium oxide to 1 mole of magnesium carbonate. And now that I've got moles magnesium oxide, I can convert to grams of magnesium oxide. 40.31 grams magnesium oxide to 1 mole of magnesium oxide. Make that actually look like an O there. Okay. Again, always good to just check grams of magnesium carbonate, moles of magnesium carbonate, moles of magnesium oxide. Everything has in fact canceled out. And I find this answer to be 23.9 grams of magnesium oxide. So theoretically, I could produce 23.9 grams of magnesium oxide from 50 grams of magnesium carbonate. Now I can go ahead and calculate my percent yield. So I know my theoretical yield, because I just calculated it, is 23.9 grams of magnesium oxide. I know my actual yield because it was given to me in the question. In lab, you would measure this yourself, is 20 grams of magnesium oxide. So percent yield (20 grams magnesium oxide) divided by 50 grams of not 50 grams, I apologize, divided by 23.9 grams of magnesium oxide times 100% gives me a value of 83.7%. That means I have a percent yield of 83.7%. So I was able to produce almost 84% of what I originally thought I would. The ratio I was able to make was almost 84% of that total amount. Pretty good, actually. This is actually quite a nice percent yield. Some reactions you'll find have a percent yield of like 30%, and that's okay for some reactions. Some have a percent yield of 90. It all depends on the reaction. But there are more examples like this in your homework, your online homework, your textbook, at the end of this chapter. Please, please, please work them. The last thing I have for you in this chapter is the following. What questions should you ask yourself? And this is the perfect picture for this because sometimes you're going to feel like this. You're going to feel like your head is going to explode. It's okay. The more problems you work, the easier these things become. I promise you. I know it probably seems overwhelming at times, and it's going to continue to feel that way sometimes. It just is. But I promise you guys, the more problems you work, the more comfortable you'll be, and the better you're going to do with this material. So always ask yourself, what is my limiting reactant? What's my access reactant? How much access reactant was left over? What's my percent yield? What's my atom economy? And is the reaction worth completing as designed? Even if I do not ask this question specifically, any of these questions specifically on a question, work the problems. If you have to, make up some numbers to be able to work that problem. If I don't give you an actual yield, but I give you a theoretical yield, pick a number. Calculate a percent yield. Any reaction you can calculate atom economy on. Go ahead and just practice. Make some problems up on your own and practice, because that's the best way you're going to be able to prepare for this class.